Okay, we're just going to have a quick look at method of sections. So this is the same frame that we used in the last video, so hopefully we'll find that we get the same answers. So the method of sections works by chopping the frame at any point, and because we're assuming that it's an equilibrium, the frame is in equilibrium overall, then it must be equilibrium at any point. So that must be an equilibrium, that must be an equilibrium, that must be an equilibrium, that must be an equilibrium. So every member must be in equilibrium. So if we chop the frame in two around about here, then we can work out what the forces are where we've chopped it and take it from there. So that's the method of sections. So we'll just go through that quite quickly, hopefully, because it means we don't have to do joint 1, joint 2, joint 3, joint 4, joint 5 to find out what's going on. And we can chop it into around here, around the red line, because that's near the middle, and so the forces at the middle will be, or the forces, at the furthest point between the two, between our two supports, will be where the forces are greatest. So if we're using the same material throughout the frame, then if the material that we're using can withstand where the forces are greatest, then that's going to be okay, isn't it? That's going to be fine. The forces should be less at the supports than they are in the middle. Okay, so we'll work his way through that. So first of all we'll trim things back to where the red line is on one side, and we'll take things from there. So we've just chopped away, just finished chopping away the oops daisy. I've chopped away the wrong line there, haven't I? No, that's fine. Okay. So that simplifies things quite a lot. We could do the other side as well, that doesn't matter. And as before, we assume that things move, that the things that we don't know are moving away. Oops, daisy, are moving away from the things. So we assume that we're in tension. So we've chopped that up there, and we've got three things that we don't know. So I'll label those up as F1, F2, F3, and I'll put some nice colour on there. So that's just tidied things up a bit. So now we apply our equations of equilibrium, so that the up and down forces must be equal and opposite, the left and right forces must be equal and opposite, and the clockwise and anti-clockwise moments must be equal and opposite. So we work our way through those three. And with the method of sections, we do have to do our clockwise and anti-clockwise moments quite often. So let's start with up and down, and we'll see how we go. So let's get that set up. So up equals down. So up, obviously, we've got reaction force 1 there, so I've just filled that in. And then down, well, we've got F2. We've got the vertical component of F2. So that's going to be sine of theta. So let's put that in a nice orange colour. So that's going to be F2. Sine theta. Okay, so that's our down component. We've nothing else going. Oh no, we do. Nearly missed that. And that's going to be plus our 20 Newton load there. Okay, so let's just put that in as well. So that's going to be black plus 20. Okay, so now the only thing that we don't know here, well, we know that R1 is 22.75. R1's 22.75 there, so we can fill that number in. So let's back up and do that. 22.75 equals F2 sine theta plus 20. So the only thing we don't know there is F2, so we can rearrange that and find F2. So let's just do that quickly. So there we've just taken the plus 20 across to the other side, plus 20 across to the other side, so that becomes minus 20, so obviously 22.75 minus 20 becomes 2.75. So there we go. Of course we can fill in that as 60 degrees there, because we're dealing with equilateral triangles in this case, so we just filled that in there as well, sine 60. So F2 equals 2.75 divided by sine 60. So we'll punch that into the calculator and we find that F2 equals 3.18. Okay, so that's fairly simple, I hope. So we found our up equals down and we found out what F2 equals. So now we want to find out about F1 and about F3. Okay, so what can we do there? Well, we found up equals down, so let's move on to left equals right and see if we can solve for that. So, going to the left then, we have, well, not that, not that, not that. We don't have anything going to the left, that's going down, so that's going up, and that's going down. So there's nothing going to the left. So on the left then, we have a big fat 0. And on the right, well, on the right, we must have something on the right, shouldn't we? So we're going right, we've got F1. So F1 is a horizontal line, so let's just copy that. We've got F1, I'll sort that out in a second, and we've got F3 going to the right as well, and we've also got the horizontal component of F2 there. So let's just fill that in. So we've just filled that in there, so we've got F1, we've got F3, and we've got the horizontal component of F2, which would be cosine theta, F2 times by cosine theta. Okay, so there are still two things we don't know here. We know what F2 is, and I'll fill that in on the next line in just a moment, but we don't know what F1 is, and we don't know what F3 is. So there are two unknowns, so we can't solve that yet. So that means that we need to move on to our moments. So let's just set that up. So now we come to our clockwise and anti-clockwise moments. And the thing we've got to remember about our clockwise and about moments is that it's a force times by a perpendicular distance. So that means a force at right angles to. Okay, so the distance, it's the distance at right angles to the force to the point we're taking moments about. So that's we've got to remember that it's at right angles to its perpendicular, because that might mean that we have to calculate some distances as well. So the first thing we need to do is select a point that we're going to take our moments about. So where are we going to take our moments about? Well, let's draw a little circle. I like drawing my little circles for our point that we're going to take moments about. And I think that that is a good point, he says. Let's try that again. I think that that is a good point to take our moments about. Okay. I think that's a good point to take our moments about. Let's fill it in there. There we go. Nice little red dot. Should we make the back? Yeah, there we are. Okay, so I think that's a good point to take our moments about, because force 1 will drop out because the distance, the perpendicular distance from force 1 to the point we're taking moments about is 0, and any number times 0 is 0. Force 2 will also drop out because that's going through the same point. Okay, so that leaves us with force 3. That's the only thing that we need to be worried about. So I think if we were pulling from F3, let me rotate. Let's see. Okay, so we can nearly see what's going on. So I think if you pulled at F3 in that direction, I think you'd end up spinning that away. That doesn't do what I thought it would. What does that do then? Oh, yeah, so that spins around there. So that should spin around there, shouldn't it? No, that spins around. I don't know. Right, anyway. There we go. So I think if we pulled around F3, we'd end up spinning that away, wouldn't we? We'd end up going that way. So that would be an anti-clockwise moment because we're going right round there. Okay, so I think we'd do that for F3, and that's the only force that we've got acting because F1 and F2 have dropped out. And 20 newtons has dropped out as well. The 20 newtons there has dropped out there, so that's dropped out. So the only other force we've got is reaction force 1. And I think if we pushed up, I think we'd end up going clockwise around that point. So we've got a reaction force 1 going clockwise, and we've got a F3 going anti-clockwise. So remember, that's a force times by a perpendicular distance. So if we're looking at the perpendicular distance, well, that's going to be perpendicular for F3 is going to be the height, isn't it? Now, just a bit of calculation here. So that's 1 metre to the halfway point. So our equilateral triangles are 2 metres each side. So that length from there, from end to end, is going to be 2 metres. So that means that the perpendicular distance from F3 to our little red dot is not going to be 2 metres. It's going to be less than 2 metres because 2 metres is our hypotenuse. So how would we find that? Well, we need to do a bit of trig, don't we? So let's set that up and find out what the perpendicular distance is for F3. So I've just done a quick triangle there. So that's what we know, isn't it? We know that our base is 1 metre and our hypotenuse is 2 metres. And we know that that's the angle between our 1 metre and our 2 metre is 60 degrees. So what could we possibly use to find out the vertical side? Well, we can use our old friend SOHCAHTOA, sine, cosine and tangent. And which of sine, cosine and tangent talks about the opposite and the adjacent? Well, it's tangent, isn't it? So let's just put in a quick tangent equation. So there we've got our tangent equation. So let's just put the numbers in and find out what this vertical distance is. So remember, this is the perpendicular distance of F3 to the point we're taking moments about. Okay, so we put our numbers in. We say tan 60 equals the opposite, which is what we want to find. That's the vertical side, over 1, which is the adjacent side. So obviously we'd take the number 1 over to the other side of the equation. So that'd be 1 times tan 60. Well, 1 times anything is itself. So tan 60 equals the opposite. So let's just bung that in our calculator and find out what the answer is. So our calculator tells us that the vertical side there is 1.73 metres. Missed a unit off, let's put a unit on. 1.73 metres. So that's our perpendicular distance from F3 to the point we're taking moments about. So now we can continue with our clockwise and anti-clockwise calculation. So we're setting up our equation now. We've got reaction force 1, which is over here, times by 1 metre, which is the perpendicular distance from the reaction force to the point we're taking moments about. And that must equal F3 times by the perpendicular distance, which we calculate to be 1.73. That's the vertical distance to the point we're taking moments about. So we'll fill in the numbers. Well, we know R1, so we can put the R1 in there in our equation. And then the only thing we don't know then would be F3. So we'll just work through that. Okay, so we've just put R1 in there, and obviously any number times by 1 is itself, so R1 remains at 22.75, and that equals 1.73 F3. So we'll just take 1.73 over the equal sign, so it becomes 22.75 divided by 1.73. So all we need to do now is just bung that little lot into our calculator, and we found force 3. So F3 then becomes 13.15 newtons. So there we go. So now we've found F3. So now we can go back to our left equals right, because we know F2, we've just found F3, so the only thing we don't know there is F1. So let's finish off this equation, and then we know all the forces acting on these joints. I'll just tidy up a bit and move that up to there, so we've got a bit of space there. Okay. So all we've done there is we've just filled in what we know. We've just filled in our F3 and our F2. So remember, F2 is the horizontal component of this force here. It's the horizontal component. Cosine 60, because it's a 60-degree triangle. Okay. So now we need to move our F3 and our F2 over to the other side of the equation, so they become minus numbers. And that leaves us with F1 all on its own. And then we can just simply calculate F1 from there. So let's go do that. And so all we need to do now is just plug this into our calculator, and we've found F1, which gives us a grand total of, and so there we found out that F1 equals minus 14.74. So if we just look back here, we said F1 is 14.72 in the opposite direction, so we got that right. F4 here, 3.175, that's our F2, 3.18. and our F3, did we calculate that? That was F2, 13.135 there, and we said 13.15. So, you know, given rounding errors, we see we get the same results. And so that's how we use the method of sections. Thank you very much.